Substring with concatenation of all words. Just going to give a quick explanation for how to do this problem. So you're given a string S and an array of strings words. All the strings of words are of the same length. Okay, so a concatenated substring in S is a substring that contains all the strings of any permutation of words concatenated. For example, if words is equal to this array of strings, then A, B, C, D, E, F, A, B, E, F, C, D, and so on and so forth. Just permutations of A, B, C, A, B, the sequence A, B, the sequence C, D, and the sequence E, F form the concatenated string, and then A, C, D, the sequence A, C, D, B, E, F is not because the order is wrong. So return the starting indices of all of the concatenated substrings in S, and you can return the answer in any order. So the starting indices of all of the concatenated substrings that show up in our bigger string S. So let's take a look at an example here. I'm going to go ahead and enlarge this, make it real big. So first of all, sort of understanding the problem. In this case, S is equal to the string bar foo, foo bar, the foo bar man. In words is equal to bar foo and the. So those three strings. So we're just looking for length 9 sequences that hold bar, foo, and the. So 3 times 3 equals 9. Bar, foo, and the in any order. So it can be the foo bar, it can be bar foo the, it can be bar the foo. As long as it's a length 9 sequence that holds these words, then that holds these strings, then we want to add the starting index of that sequence of 9. So for example, if we start taking a look at over here, 0, 1, 2, 3, 4, 5, 6, we can see 6 is one of the outputs, right? So 6, foo, bar, the. This 9 sequence creates, it falls under, satisfies this requirement. And then we see that for 9 as well, up here. Bar, the foo. This time the order is bar, and then the, and then foo. Also satisfies the sequence. And then 12, the foo bar. Okay? And then sequences that obviously don't work. Foo bar man does not work. Does not have the word the in it. Bar foo foo does not work. And then obviously we can look at this. What if this starting sequence is right here? Ufu Bart also does not work. It's a sequence of 9, but Ufu Bart, it does not have oof, it does not have oob, it does not have art. So starting out looking at this problem, kind of the initial intuition you can sort of have is, okay, we want to find every single viable answer will be of length, words.length. So the length of words, words multiplied by the length of every single word inside of words. So words I.length. So like a length of words at the 0th index. And as we can see up here, all strings of words are the same lengths. So as we concatenate them, we know that the sequence that we desire will always be of length 9 in this case. So if we're to sort of take a look at what that implies for us, we can first just start with an approach where we just always look at 9 characters at once. So first we look at the first 9 characters, bar, foo, foo. How might we be able to figure out if this bar, foo, foo sequence satisfies all of the words inside of words? One way we could do it is we could just iterate through the entire sequence, right? We can iterate through bar, foo, foo and match up the letters with the words. That would take O of, and if we were to say n is equal to the length of S, and then let's say k is equal to the length of words. If we were to go with an approach like that, where we simply look at every single 9-letter sequence, so we look at bar foo foo, and then we look at arf oof oob, and then we keep on going down all the way to the end of S. So we keep on going down until we reach the very end. That runtime would look something like O of n times k, right? Where k is the length of words, because we have to iterate through words every single time. So obviously in some cases that's okay, but let's try to optimize from here. Let's try to be able to figure out a solution that can solve it in a slightly faster way. So right off the bat, we can sort of tell that this is kind of like a sliding window problem, right? If we were looking at these 9 letters right here, bar foo foo, and we see that over here, bar foo foo does not match up. When we check the next sequence, arf, oof, oob, we can just, instead of reconstructing all of the letters, we can just say we take the B off and then add the new B. So we always just take this letter off and then add the next one and then do that over and over until we reach the end. And so we're doing each operation in O of 1. However, for this problem, this approach still doesn't quite work because we still have to check all of arf, oof, and oob, and then erf, oof, urfo, ofo. We have to check all of these sequences against words every single time. So we have to sort of come up with a way to be able to instantly tell whether a sequence satisfies words. So one way we can sort of think about it now is, instead of adding just one letter at a single time, what if we try adding 3 letters at a time, in this case to match the length of each word inside of words? So this sort of intuitively is a kind of makes sense as an approach, because like let's say we were looking at bar first. Let's say we're going with a sort of sliding window approach where we had the left side of our sliding window as L and the right side of our sliding window as R. So L and R both start at the very beginning of the string. So I'm going to reconstruct it slightly bigger this time. Foo, bar, the. So that's enough for now. If we were to sort of take a look at what might happen here. If this was the left of our sliding window and this was our right, I'm going to start them at the same index. What if we just try incrementing by 3 every single time, rather than incrementing by 1 or incrementing by 2, but increment by the length of each word? Because now what we can do is we can look at each 3-length segment at a time. And then we can check if this 3-length segment appears in words. And one other small optimization we can make in the form of pre-processing is, in the very beginning, before we do any sort of computation, we query all of the words inside of words and put them in a hash map that contains strings and integers. So this string just represents what the string is at that as the key. And because there can be duplicates, this integer just tells us how many of that string there are. So for us to be able to sort of satisfy the requirement now, we can see, okay, if our hash map lines up with this pre-processed hash map, if it has all of the same words, because obviously sequence doesn't matter, if all the words match up, if bar, foo, and the, if there's one bar, if there's one foo, and there's one the, then we know we're good. Then we can add that index. So now here, if we increment by 3, we can say we start at index 0, 0, 1, 2, 3. We look at this substring right here from 0 to 3 or 0 to 2, and we say, is bar in our hash map? So our hash map right now, in the very beginning, will sort of look like this. So the key is bar, of course it's lowercase characters. Bar, foo, and the 1, 1, 1, right? And so we're gonna do something where if our hash map ends up being empty, then we know we've created a full sequence. And so we're just sort of doing it backwards because it's easier that way, because we can instantly figure out just with like dot size, figure out if our hash map has any more items left. So in the beginning, before, as L and R are still, as the left and right sides of our window are still at the very beginning, we look at R and we look at this substring, bar. Is bar in it? Yes, it is. So we decrement it to 0. In this case, we can just delete the item. We can remove bar from our hash map, but just for this sake of this problem right now, I'm not going to do that. So then R comes up here, and we look at R again, because we want to look at this sequence now. Because now if this sequence contained the viable answer, or if this sequence, 3-letter sequence right here, is contained by the hash map, then we can add it as well. So it is. So we continue. And then we go up here. And then we look at foo. Does foo occur? No, it does not. Right? So now what we need to do is, we know that this sequence will never create a viable sequence. We know that this starting L value at index 0 will never be able to create a 9-length sequence that is valid, simply because we've met an obstacle. We can't get past this. It has to be in order of bar, foo, the. So this next one had to be the. Otherwise, there's no point in continuing searching down this way. So once we meet this obstacle, once we see that foo is no longer in our map, we can actually iterate L up, because we know that there will be no answer where the starting index is at 0. So now, instead of incrementing up to 1, we increment up to 3. So now L is up at foo. And when we increment L, we have to be careful, and we have to make sure that when we increment L, we're now looking at this sequence right here. So we have to add bar back into our old, back into our hash map, because our hash map sort of represents what words do we still need to visit for us to create a valid sequence, a valid 9-length sequence. So once L is incremented up, this bar is no longer part of our running sequence anymore. So now L and R are up here. So now we have foo and we have foo. Is foo, we look at R again, is foo, so this part right here, the next word, is it inside of our map? No, it's not. So we can actually increment L up again, right? So now L and R are both up here again. So the reason why we can just do that is because, once again, same logic. When the L was back here, it was blocked by this obstacle, meaning we know that there is no index 3 that we need to return. So we can just increment L up to continue our search space, or continue searching the rest of our search space, right? So now we're back to square one. we're not back to square one. We've iterated through 5 items already, 6 items, and we know that none of these work. None of the 0 and 3 does not work. We still do not know if 1, 2, 4, 5 works yet, but we'll get to that in a second. So now, when we look at foo, it does work, right? Because we've added foo, the counter, back in when we incremented L. So now this gets to go back down to 0. And now we can start moving R up. So as R moves up, now it's over here. Is there bar? Yes, there is. R moves up again. Is there the? Yes, there is. And now it's over here. There's some more letters over here and whatnot, but the process continues. Here, once we increment R up to here, we see hash map size is, or hash map is empty. Once we see that it's empty, we can add this index right here to our answer. So our answer would just be a list of integers, and we just add this index 6. We add L. Okay? So we do this all the way to the end, and this procedure runs in O of n time. If you're familiar with sliding window, it will always run in O of n time because it's just 2 pointers. At each stage, we're just running the pointer, either the left pointer up or the right pointer up, or both of them in some cases. And because it's just 2 pointers iterating through, it'll just be O of big O of 2n, which is just O of n. And in this case, we're actually going by 3, but it's still just O of n, right? That's the time complexity here. And then once we hit this point where we get a fully good sequence, what we can do is, we know there will be no more valid ones here at L anymore. So what we can do is we increment both L and R. So if we hit a valid sequence, we can just increment L, increment R. Both of them go up at the same time. I don't have any more space for R, but you get the point. The R will be at the next. We'll increment by 3 as well. And then every single time we increment L, make sure we add back to our hash map. Every time we increment R, we remove from the hash map if that sequence, the new sequence that R just added, the 3-letter sequence in this case, is contained in the hash map. Otherwise, increment L. And let's say, for example, if L and R are both here, and there is no bar in our hash map, this sequence bar is not contained in our hash map, then still pretty easy. We just increment L and R at the same time as well, because we know if bar isn't there, then it's just not going to work. So after we figured this out, we still have to take care of the cases where L starts at 1 and L starts at 2 and L starts at 4 and 5. But what you sort of notice is we can just do this exact same sliding window process again, but just with a different starting point. So first we start at 0. So LR starts at 0. Then for our next iteration, LR will start at 1. And it'll still increment by 3 every single time. And then it'll start at 2. And it'll still increment by 3 every single time. And then we actually just stop at 3. So we don't go here anymore because that would be repeating back here, right? We don't need to repeat that. So we just do it in this case. We do our sliding window procedure n time, or 3 times, which is just equal to the length of each word here. So ultimately our runtime would just be O of n times k, where k is s dot length, or n is s dot length, and k is the length of each word inside of words. So this is a much better runtime, especially if words is very long.